Hey guys, this is Coach Lowe and we are starting Chapter 2, Section 1. This is Geometry, Inductive Reasoning, and Conjecture. So place these in your definition section. Make sure you label this Chapter 2. So we'll start a new page on our definitions. Inductive Reasoning. Reasoning that uses a number of specific examples to arrive at a conclusion. And we'll do some of that. We'll look at examples and patterns, and then we'll make a conclusion about it, which is using inductive reasoning. The conclusion that we make is called a conjecture. And so that's the second definition. And then counterexample will be if we have a conjecture, we're going to try to find something that doesn't work. So that's a counterexample, something that proves that a conjecture is not true. So if you need to pause the video and go back and write those definitions down, please do so. So example number 1, we have 4 examples here. Write a conjecture that describes the pattern in each sequence, then use your conjecture to find the next item in the sequence. Let's do number 1 together, and then you guys can pause the video and roll through the next 3. All right, so we want to look for patterns. So we see 3, 6, 9, 12, 15. So my numbers are increasing by 3 each time, or it's the first term multiplied by 3. So first term times 3, and then this is my term number, my second term times 3, my third number times 3. So several ways to look at that. Increasing by 3 each time. Or we can think about term number. This is the first term, the second term, the third term, and so on. And so it's 1 times 3, 2 times 3, 3 times 3, which means n times 3 each time, or 3n. So we can write our conjecture increases by 3, increase each term by 3, or it's 3 times n, where n is my term number. All right, so the next term in the sequence would be 18. All right, I don't care which way you describe those, but we will move from saying words like this to putting it in an expression like that. All right, so you can use words on 2, 3, and 4. Pause the video, and I'll be waiting on you. All right, so now we're going to start with number 2. Number 2 says 3, and then 33, and then 333, and then 3,333. So you can see that they're increasing a digit each time. So first we have a 3 in the ones place, and then we include a 3 in the tens place, and then in the hundreds place. So the next one, there will be a 3 in the thousands place. So 3,333. So my conjecture on that one, you may have written it in a different way than I did, and that's totally fine. But you may have written something like each number has a 3, an extra 3 in the digit, or they include another 3 in the digit. Totally fine. Different ways to write that. All right, let's look at number 3. If you looked at increasing, it increases by 3, and then 5, and then 7, and then 9. So we're increasing by odd numbers each time, and that's fine. That's a good pattern. But we also have numbers that are squares, right? Perfect squares. So I have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. The next one would be 6 squared, so I would have 36. So my conjecture would be the term number squared, or if you put increasing by the next odd number, or adding the next odd number each time, that's okay too. Like I said, we're going to move from this stuff to this during this class. So awesome. All right, let's look at the next one. 1, then 1/3. I'm going to write it like this so you can see it maybe a little better. And then 1/9, and then 1/27. Maybe you picked up on with each one we're multiplying by 1/3. The denominator is being multiplied by 3 each time, which means either we're dividing by 3, you can say it that way, or multiplying by 1/3. All right, so 1/81st would be a good one for that one. All right, let's keep going. All right, so the next one, make a conjecture about each value or geometric relationship. 1 more than the product of 2 and a number. So when I write this, what would be, or when I figure this out, what would be the conjecture that I would make? So let's start with a product of 2 and a number. So I'm going to multiply a number by 2 and then add 1 to it. Multiplying a number by 2 each time forces the number to be an even number. So when I do this, 2 times an odd number makes it even. For example, if I take 3, I multiply it by 2, I get 6. When I double it, even an even number, when I double it, I get an even number. So multiplying by 2 forces an even number, and then when I add 1 to it, it forces it to be odd. So every number that this thing spits out will be an odd number. So the result of this the resulting number will be odd. And you can write that different ways. It doesn't have to be exactly my words. You can write it different ways, but my answer will be an odd number. The relationship between x and y, if the product of x and y is 0, or in other words, if I multiply x and y together, I get 0. The result is either x was 0 or y was 0 or both, right? Right? So either x is 0 because 0 multiplied by anything that y is 0, or y is 0, or both. All right, the relationship between a and b, if a plus b is 0. A and b are opposite numbers. A and b are opposite. They have to be. Like 5 and negative 5. 1/4, negative 1/4. Negative 16, positive 16. If they add to be 0, they are opposites. The relationship between the angles of an equilateral triangle. So if all sides are equal, what do we know about their angles? If all sides are equal, then their angles are equal. All angles are equal in measure or are congruent. All right. Last thing, let's look at counterexample. So we're going to decide if this conjecture is true or false. And then if we think it's false, we just have to have one example that won't work to prove that it's false. So one example. So this is a good way to learn how to debate with somebody. If they say always, you always do this, one counterexample. This time I didn't do that, therefore you're wrong because you said always. It's a fun way to argue. All right, so number 1, don't try it on your parents. That's a bad idea. You'll get grounded. If b is an integer, then the opposite of b is negative. Okay, integers. Integers are whole numbers. Oops, I changed the color. Sorry. I got to quit putting my hand on the tray here. Whole numbers and their opposites. Okay, so it says if I pick one of these numbers and I take its opposite, the result is negative. Well, that's true as long as I'm here. It is not true, however, if I am here. There is no opposite of 0, and the opposite of negative 3 is positive 3. So there is my counterexample. This is false because I let b equal 3, negative 3. When b is negative 3, or any negative number for that matter, this is false because it spits out a positive number. All right, if you have 3 points, S, R, and T, then they are collinear. If you have 3 points, S, R, and T, then they are collinear. Well, okay, that's false. There are 3 points, S, R, and T, and they are non-collinear. Right, so that is not true. I could have 3 points that are not on the same line. Collinear means they all lie on the same line. There are 3 that don't. All right, if 2 angles are supplementary, that means add to be 180. So you may have to look some of these up. Add to be 180 degrees, complementary is add to be 90. Then they form a linear pair. Well, that could be true, but it's not. It doesn't necessarily have to be true. 2 angles could be supplementary and not be connected. They don't even really have to be right next to each other like I drew them. But you can see, I just want you to see this. If you smush those two together, they would form a linear pair. But they do not form a linear pair here because they don't share a vertex and they don't share a side. So I'm going to say this angle measure is 30 and this is 150. They are supplementary. The sum of those two will add to be 180 degrees, but they are not a linear pair. All right, guys, that's it. And I will see you soon. This is Coach Lowe and I'm out.